Welcome back to G Fun Facts Online. Today we are diving deep into a topic that sits at the uncomfortable intersection of modern warfare, international trade policy, and the physics of light. We are talking about the concept of trustworthy hardware, and specifically, the rise of geo-locking in semiconductor supply chains. To understand why this is becoming the most critical conversation in the tech world, we have to start not in a Silicon Valley boardroom but in a war zone. In May 2022, the world watched the chaos of the Russian invasion of Ukraine. Amidst the shelling and the troop movements, a very specific, quiet skirmish took place in the city of Melitopol. Russian troops had seized an agricultural dealership and loaded up 27 pieces of high-tech machinery. We are talking about massive John Deere tractors and combine harvesters. This wasn't just farm equipment. This was six-figure, precision-engineered hardware valued at over $5 million. The troops loaded this loot onto flatbed trucks and transported it nearly 700 miles away to Chechnya. The plan was obviously to use this equipment to bolster their own agricultural output. But when they arrived in Chechnya and attempted to fire up the engines, nothing happened. The machines were dead. They hadn't been sabotaged with sugar in the gas tank. They hadn't been physically dismantled. They had been bricked remotely. A signal sent from thousands of miles away had turned these sophisticated industrial tools into useless piles of iron and plastic. This incident was a watershed moment. It was a stark demonstration of geo-locking, which is the capability to restrict a piece of hardware's functionality based on its physical location. While this technology saved a dealership's inventory from being used by an invading force, it opened a massive Pandora's box for the global semiconductor industry. It forced a question that everyone from Washington to Beijing is now trying to answer. If a tractor can be remotely disabled because it moved across a border, what about a server? What about a medical device? What about the AI processor running a power grid? As geopolitical tensions rise, specifically between the US and China, the concept of trustworthy hardware is evolving from a niche security feature into the central pillar of global trade. We are entering an era where chips don't just compute, they obey. To understand the gravity of this, we have to look at the phenomenon known as the Great Decoupling. For the last 40 years, the semiconductor industry was the poster child for globalization. A chip might be designed in California, using intellectual property from the UK, manufactured in a foundry in Taiwan, packaged in Malaysia, and finally sold in a device in Germany. It was a seamless, borderless flow. But as nations scramble to secure their supply chains, that model is dying. The United States has taken the most aggressive stance with the introduction of the Chip Security Act in mid-2025. This legislation represents a total paradigm shift. Historically, export controls were paper-based. A company would sign a document promising not to sell a sensitive chip to a restricted entity, and the government would trust that paperwork. The Chip Security Act says that paper is no longer enough. The logic is simple. If you cannot trust the paperwork, you must trust the silicon. The Act proposes that advanced chips, specifically those used for artificial intelligence and high-performance computing, must carry built-in mechanisms to verify their location. Imagine an H100 GPU meant for a data center in France. If that chip is diverted and suddenly comes online in a restricted facility in Shenzhen, the hardware itself is designed to realize it is in the wrong place and degrade its performance or shut down entirely. Across the Atlantic, the European Union is taking a slightly different path with the European Chips Act. While the US is focused on using these locks as a choke point to control adversaries, the EU is focused on resilience and surveillance. Their semiconductor alert system is designed to map supply chains, but European policymakers are terrified of Trojan horses. Their concern is ensuring that the hardware powering Europe's energy grids and hospitals doesn't have a foreign kill switch hidden inside. This brings us to the engineering challenge. It is one thing to write a law saying a chip must know its location. It is a completely different engineering challenge to teach a piece of silicon geography. How do you make a rock know where it is? Engineers are deploying a suite of technologies called hardware-enabled mechanisms, or HEMS. The most obvious method is embedding a global navigation satellite system, or GNSS receiver, directly into the device. This is exactly how John Deere disabled those tractors, and how Starlink terminals restrict service in unauthorized regions. But for high-security chips, GPS is actually a terrible solution. GPS signals are weak. They struggle to penetrate deep indoors where servers usually live, like basements or shielded data centers. More importantly, GPS is easily spoofed. You can buy a device for a few $100s that broadcasts a fake GPS signal, convincing a receiver that it is in Kansas when it is actually in Tehran. To solve this, engineers are turning to physics. Specifically, they are using ping-based triangulation, also known as delay-based location. This relies on the one universal constant we can trust, the speed of light. Light, and therefore data, travels at a finite speed. It is physically impossible to fake being closer to a server than you actually are. If a chip claims to be in New York, but it takes 200 milliseconds to ping a server in New Jersey, the system knows it is lying. The physics simply don't add up. By measuring the latency between the chip and several known landmark servers around the world, the chip can triangulate its position with a high degree of certainty that cannot be spoofed without breaking the laws of physics. But knowing location isn't enough. You also need to know identity. This is where physically unclonable functions, or PUFs, come in. Think of a PUF as a biometric fingerprint for a microchip. When chips are manufactured, there are microscopic random variations in the silicon structure. No two chips are exactly alike, even if they come from the same wafer. A PUF uses these variations to generate a unique digital key that cannot be cloned, not even by the factory that made it. When you combine a PUF with a location check, you get a powerful lock. It prevents adversaries from swapping a locked high-end chip with an unlocked lower-tier chip, because the software license is bound to that specific atomic structure. For systems that aren't connected to the internet, engineers are looking at time-bound offline licensing. This works like a digital lease. The chip works for 30 days, and then it requires a digital handshake or a new cryptographic key to continue functioning. To get that key, the user has to verify their physical location, forcing a periodic proof of geography. However, history teaches us a very important lesson. For every digital lock, there is a digital lockpick. The move toward hardware geo-locking has reignited a high-stakes game of cat and mouse between multi-billion-dollar corporations and decentralized hacker communities. We saw a preview of this in 2021 during the crypto mining boom. Gamers couldn't buy graphics cards because miners were buying them all. NVIDIA responded by releasing light hash rate cards. This was hardware designed to artificially halve the performance if it detected crypto mining algorithms. It took less than a year for that lock to be obliterated. First, hackers found a driver leak. Then, groups like NB Miner unlocked 70% of the performance. Finally, the NiceHash group managed a 100% unlock. The lesson was brutal but clear. If the hardware physically possesses the ability to do the math, software locks are just temporary speed bumps. We are seeing the same thing with Starlink in war zones. SpaceX's internet terminals are geofenced to prevent use in unauthorized countries. Yet, reports from 2024 indicate a thriving gray market. Users in unauthorized regions, including parts of Africa and Russian-occupied Ukraine, have managed to bypass these blocks. They use GPS spoofing kits to feed false coordinates to the dish, or complex routing tricks to mask the traffic's origin. It proves that geofencing is often porous. We are likely heading toward a resurgence of the mod chip era of the 1990s. Just as gamers used to solder chips onto their PlayStations to play imported games, nation-states will likely invest in interposer hardware. These would be physical devices that sit between the chip and the circuit board, feeding it fake timing signals, spoofed GPS data, and emulated heartbeats to keep the geo-locked processor happy. This transition to trustworthy hardware is not just a technical puzzle, it is an ethical minefield. The most immediate risk is the concept of bricking. Imagine a hospital in a developing nation that buys a second-hand MRI machine. If that machine was originally sold to a clinic in Germany and the manufacturer's geo-lock detects the move to a new country, the machine could refuse to turn on. The hospital has paid for the hardware, but they don't have the geographical permission to use it. For regular consumers, this could mean your smart laptop refusing to boot because you took it on vacation to a country on a watch list. The friction for legitimate commerce could be immense. This also fundamentally changes the concept of ownership. Farmers have been at the forefront of this battle. Because John Deere locks its tractor software, American farmers were ironically forced to buy hacked firmware from Ukrainian hackers just to repair their own equipment. As geo-locking becomes standard, the right to repair movement will likely morph into a right to unlock movement. Owning hardware becomes a legal fiction if the manufacturer retains the power to disable it at will. Furthermore, we are risking a future where the Internet of Things is balkanized, creating a splinternet of things. We can envision a scenario where a Western smart car might not start if it detects it has been shipped to an Eastern Bloc country. Conversely, China may mandate that no Tesla can enter sensitive government zones unless its cameras are hardware disabled. This creates a supply chain nightmare. Manufacturers might have to build separate red chips for one market and blue chips for another, destroying economies of scale and driving up costs for everyone. Looking toward 2030, the landscape of semiconductor supply chains will be defined by distrust. We will likely see mandatory telemetry, where high-end chips require a constant heartbeat connection to the vendor's cloud to function. Offline computing may become a premium, regulated luxury. In response to locked-down Western chips, we may see an explosion of investment in RISC-V and open-source hardware architectures. Nations like China, Russia, and India will be desperate to avoid foreign kill switches, leading to the rise of sovereign silicon. We will also see the emergence of auditability as a service. Third-party companies will exist solely to audit chips for hidden locks, and certified lock-free may become a major marketing feature for chips sold to neutral nations. In conclusion, the geo-locking of semiconductor supply chains represents the final death knell of the neutral technology myth. Hardware is no longer just a tool, it is a policy enforcer. For the US and its allies, this offers a potent weapon to safeguard national security and intellectual property. For the rest of the world, it is a stark reminder that if you don't control the silicon, you don't control the switch. As those John Deere tractors rotting in Chechnya proved, in the 21st century, possession is no longer 9/10 of the law, connectivity is. Thanks for listening to G Fun Facts Online.